So looking at that K value, this is lecture number 2, by the way, for chapter 15. Looking at the K value, it tells us a lot about the reaction. So if I look at a K value and I see it as something greater than 1, whoops, let me go back here and change my cursor over. I want to use the felt tip pen. There we go. So if my value is anything greater than 1, that tells me that my products are favored. So the numerator is greater than the denominator. And just the opposite. If my K value is less than 1, that tells me that I have more reactants, and it doesn't shift so much to the right towards the products. Easy enough. Something else in regards to the values that we have here. This isn't really going to go anywhere, but we'll mention it at least. We have these two equations here that are just opposites of each other. We have one going the forward direction, one going the reverse direction, depending upon how we express this. So normally we're going to say this is just how we normally do it. So we end up with a K value, enough said. But if we want to express and say, well, you know, I'm really more interested in the other way around, you know, the NO2 over the N2O4. I'm really concerned or more interested in how that reaction is going to go. I said that incorrectly, but I'm more talking about this reaction here. It's simply the inverse. So depending upon how you set up the reaction, that is going to dictate the value of the K. So it just depends how you look at it. One is the inverse of the other, that's all. Excuse me. Another thing you can do is, depending upon how the reaction is put together, you may have to manipulate it in such a way that it actually shows these values are twice the values of the original equation. This is extremely rare. I really don't see this coming up at all. But just to mention, based on how the equations are put together, notice again that this value is given as the coefficient in the general equation. So the exponent is going to reflect that. So that is going to have an impact on the value of the K value, because it is going to be squared in this case, as opposed in the previous one it was not. Okay? Moving on. Just to mention that something else in regards to changing the equations around. So far we've been looking at it from the standpoint that everything's just been an elementary step. There's only one step in the entire reaction. You can have more. And if there are more, what you're ultimately going to end up doing is multiplying the K values by each other. So getting a product of the two. And if you set them up, I don't know if we'll have, no, I don't have an example of that. It would just simply be the product of all of the products over the product of all of the reactants. And that sounds really difficult, but we'll take a look at that in class. Okay, heterogeneous equilibriums. Not everything is going to be a gas or a solution. Sometimes you're going to have pure solids and pure liquids within the reaction. And that's going to be a really big basis when we get into chapter 17. Maybe a little bit 18, but mostly 17. When we're looking at, I said, yes, chapter 17. When we're looking at one of these equations, the concentration, this is what we're talking about. When we're looking at the concentration of a pure solid, it just is what it is. It's really a value of 1. And the same thing for a pure liquid, which is water. It's just a value of 1. So it doesn't really have any impact on the K value, the equilibrium constant. So we can swing it on over to the K side of the equation, but it's really not going to have any impact. So we pretty much ignore it. And we'll see an example of that right here. So here we have some lead chloride, which is going to dissociate in water. Maybe it's not necessarily 100%. It's going to dissociate to a certain degree. And that's expressed in the K value. So how much of this lead chloride is going to dissolve in water? This K value kind of gives us an indication of how that goes. But notice I don't have this sitting over the concentration of lead chloride solid, because again, it really doesn't have a concentration. It's just 1. So we kind of just multiply that, and it's sitting somewhere over here on the left hand side, but we don't write it. Easy enough. And we talked about this once before in regards to saturated solutions. Here we have an equation where we have some calcium carbonate, solid, and we also have some solid calcium oxide sitting here on the right. As long as I have some of these, just some, it doesn't matter how much, a little or a lot, it doesn't matter. We can see this in both of these examples down below. We can ignore it. As long you have to have some present in order to have this equilibrium set up with the carbon dioxide, but as long as some is present, it has no bearing. You're going to have the exact same concentration of carbon dioxide. So if we wanted to say, well, what happens if I put a lot more calcium oxide into this equation? Nothing. As long as I have some, doesn't matter little or a lot, it's going to be the same concentration of carbon dioxide. Alright, so some calculations. Given your reaction, here we have H2 plus I2 giving us 2HI, we have some initial concentrations. So we see one written right here, and we see the other one written right here. That's all we have to start off this equation. We notice listed here at the end, we have a final equilibrium concentration of the product. Sounds like a lot. These are pretty easy reactions, and you guys will do quite a few of these. So here's our equation, and just to kind of rewrite this, we have H2 plus I2 giving us an equilibrium of 2HI. So as we saw in the previous problem right here, this is our initial concentration of the H2 and I2, and I don't have any HI. So I kind of breezed over it, didn't really mention it here. Most of your books are going to list this as an ICE equation, where you have an initial concentration, a change in concentration, and an equilibrium, so the E, ICE. When I was in college, I remember these being expressed as a Rice equation for the reaction, because you're going to have a reaction. You can't do it, so I don't know why they don't put the R in there. Anyways, moving on. So this is our given information, and we do know that the ending equilibrium value of this is sitting right here. So I have to determine, all I want to do is write an equilibrium expression, so I need a value right here, and I need a value right here. Well, if this is produced, that means I had a change, which I gained some of this value right there. Well, where did it come from? Well, it had to come from these guys. But you have to remember what the stoichiometry is. This has a value of 2, this is a value of 1, and this is a value of 1. So when we do our stoichiometry, we have to take into account these values. So these are going to be expressed as half as much of this value, doing the math. So I'm actually losing this amount of each of these reactants and getting a new value of that. So again, I already knew I had this. So in writing an equilibrium expression, what is my K value? Well, here's K, and this is the equation that I'm starting off with. All I have to do is plug in the values for what they are. Don't forget the exponential values, whatever the coefficients were in the equation. And you end up with a value of 51. And 51 is greater than 1, so it tells me that products are favored. The reaction pushes more so to the right. And you can put any values you wanted in here for concentrations, as long as it has to obey this value. So we'll get more into that in a second. Okay, so the reaction quotient. What that tells us is, okay, you didn't start off at some perfect set. You're not at equilibrium. So that 51 value right now doesn't exist. You're some other value. You may be greater than 51, you may be less than 51. So ultimately, if this reaction does come to equilibrium, it is going to be 51, because that's how this reaction kind of plays out. So what happens with Q is it's going to have to move. And when I have a Q value, you could ask yourself the question, what's going to happen with the reaction? Well, it's going to move to K. So for example, if Q is less than my value that I need, that means the reaction is going to push towards products. If my value of Q is greater than, then it's going to push towards reactants. Easy. And I'm just going to breeze on by the rest of this. We already went over that. All right, this is a good place to take a break, and we'll finish up with one more lecture.